In this video, we'll look at the fundamental theorem of calculus. So the fundamental theorem of calculus is just that, fundamental and amazing. It is the theorem that makes the formal connection between the two main pillars of calculus, derivatives and antiderivatives, or integrals. Okay? And we'll see that when we actually use it, it is quite amazing. So let me show you exactly what it is, and then we'll do some examples. So we call this thing the FTC for short, and really it says the following. It says that if f, so my function f is continuous, on some x interval a, b, okay, from a to b, and capital F is the antiderivative. It's the antiderivative of f. Then I have the following. The following expression. It's a connection between the integral or antiderivative part of calculus and the derivative part. That is, we have the following. Then we have that if you integrate from a to b, or you find the antiderivative from a to b of my function f of x dx, it's exactly equal to the antiderivative at these values, the difference of the two. In other words, it's f of b minus f of a. That's exactly the fundamental theorem of calculus. And again, what it says is, if I want to compute the definite integral of my function f, in other words, I want to know the area underneath the curve f between points a and b, it's exactly equal to the difference in the antiderivative at the values b and a. Okay, so it's capital F at b minus capital F at a. And this is amazing because it gives us a real connection between the integral part of calculus over here and the derivative part of calculus, which is over here. Okay? Keep in mind that, of course, by definition, f's derivative at x gives me my original function back, right? Because that's what it is. It's the antiderivative. So here's the fundamental theorem of calculus. Let's actually put it to work. All right, so here it is. Here's a simple example using the fundamental theorem of calculus. That is, I want to compute this definite integral. Again, with a definite integral, we want a number as an output, not a function, because it's definite. So to compute the definite integral, all I need to do is to determine the antiderivative and then plug in the endpoints. That's what the fundamental theorem of calculus says. That's amazing. That means I don't care about any other point along the line, just the endpoints. This is why we spent so much time talking about antiderivatives, so we can compute things like this. This one's easy because we know the antiderivative of polynomials. So let's go ahead and compute. And we can do this in the same way we did before, which is all we need to do is take this constant out front and deal with this as an antiderivative. Even if we have sums or differences, we can do the same thing. We can break it up into small pieces, just like before, no different. The only difference is that in the end, we have to plug in values to get an actual number out. So let's compute. Here we've got a 5. We've got this integral or antiderivative sign here, -1 out to 3, t squared dt. But we know the antiderivative of that, right? We just add 1 to the power and divide by what we found. So this is really 5. It's going to be 1/3 t cubed inside. And then what I draw is a symbol that just means that I need to plug in the endpoints. So this symbol just means I need to evaluate at 2 points. And on the bottom, I'll put -1. On the top, I'll put 3. So the bar just means I'm evaluating here and here. And so what I have here is, since this is the antiderivative, right, I've certainly computed that capital F of x, the antiderivative of this, is 5/3 t cubed. Right? That's the antiderivative, or at least the antiderivative that matters in this problem. Okay? So for this, because we're talking about a definite integral, we determine whatever constants would be there. So this is the antiderivative that we care about here. And what I have is, I just need to evaluate this value at these 2 points, right? So I'm going to put b in first. B is 3, right? This is b. This is A. So I have 5/3. I got to put B in, so that's 3 cubed minus plug in A for T. So I have 5/3 A. A is -1 cubed. Okay, and all I have to do is compute these values, and I'm going to get a number out. That's what I want. So let's continue and finish. What we have here is, well, this is 3 cubed. One of those 3's is going to cancel, and I'm going to get a 9. So 9 times 5 is 45. Minus, well, -1 cubed is going to be -1. So actually, the -1 is going to make this a positive. So we're really just going to get a positive here, and you're going to have a 5/3. So if we want an exact value, let's put it into one complete fraction. And we just turn the 45 into thirds, and 45 into thirds becomes 135/3. And so putting that together, you're going to have 140/3. So when all the smoke clears, my answer is 140/3. So this is the exact value of the area below this particular curve from -1 out to 3. Okay? And so we know the picture of what this kind of looks like. It's really some kind of quadratic function. And all I'm saying is that if we start at -1 and go out to 3, the overall area beneath that curve, above the horizontal axis, will be this value, 140/3.